Again, thank you very much for joining our webinar, Understanding Datasheet Thermal Parameters and IC Junction Temperatures today. I'm Julian Meyer, Marketing Manager at MPS. In this webinar, automotive application engineering expert Ralf Omberger provides a foundation for understanding how to think about thermal management more intuitively and help you to achieve cool running, cost-optimized solutions. Now a bit of housekeeping before we start our session. All attendees are on mute. Please ask any questions via the Q&A button located on the bottom of the Zoom meeting interface. Questions will be answered at the end of the presentation. Maybe it makes sense that you make a note during the session, and then we will come back at the end of the session and make sure that we address it. We are recording the session, and it will be available on demand within the next couple of days. We will also provide a PDF of the actual presentation itself. Again, thank you very much for joining our session today, and I'm handing over to Rolf now. Rolf, the stage is yours.
Okay, thank you, Julian. Hello, everyone. My name is Ralf Omberger. I'm Applications Engineer at MPS. Our webinar today, Understanding Datasheet Thermal Parameters and IC Junction Temperatures. Our agenda today, we talk about electrothermal analogy and their equations for electrical and thermal analogy. Thermal resistance theta in a datasheet. We explain theta and psi. We show calculations with thermal networks and layout recommendations. And finally, the conclusion and the questions and answers. Introduction. There is much confusion about datasheet's thermal resistance parameters. This introductory webinar will help to understand the thermal parameters found in datasheets, theta and psi, how to calculate, and most importantly, how to apply these values to a design. We describe the relationship between application ambient temperatures and how they compare to PCB temperatures or IC junction temperatures. We discuss how power dissipation changes with temperature and how to achieve a cool running, cost-optimized solution. Electrothermal analogy. There are certain analogies that can be made between thermal and electrical quantities. The table compare electrical thermal quantities and their material constants. We see here on the left side the electrical quantities, well known for electronic engineers: voltage, current, charge, capacitance, resistance, with the formula symbol and the unit. And the analogy, for example, for voltage is the temperature difference measured in Kelvin. For current, the heat flow. For charge, the heat quantity. Capacitance, resistance, the thermal resistance. The conductance, thermal conductivity. So when you know how to calculate with currents and voltages, then you also know how to calculate with thermal quantities. It's just the same. We see a table with thermal material constants and variables for different materials. You see here well-known copper. It has a very good thermal conductivity of 388 watts per meter times Kelvin. The worst one is air. You see the small number compared to copper, and in between different materials. Aluminium 205, silicon only half of copper, and the solder thin is even half of the silicon it's bad compared to copper. So keep this in mind for your design. A solder junction is not a good thermal conductivity, but there is nothing else you can do. You must fix the IC on the PCB. And also here, the mold compound, it's not very good. The mold compound is the plastic around the IC. And the PCB itself, for standard material, it's also very poor compared to metal. We see a table with material constants and variables for different materials. Here is the specific heat capacity of water is the highest, copper 10%. But these numbers, they are only important in case you have a heat sink, a large one. It's they're becoming important when you for the thermal transient response. In the steady state, that doesn't matter anymore. It is important to know electrical and thermal quantities can be calculated in networks. They are comparable to Kirchhoff rules. We know the basic electrical equations. For example, here, the series resistors, parallel resistors, capacitors, and the current here. The equivalent exactly for this equation is the addition of thermal resistors. Paralleling is the same. And for the transient calculation, if you want to do it, you can use the thermal capacity. It's like a capacitor. And the heat flow, it's the same like the electric current. Just the same mathematic behind. Theta is the thermal resistance, and it is specified in a datasheet junction to ambient and junction to case. We see here a snippet from the MPQ 4572, a DC switching power IC from MPS, as an example for understanding thermal parameters in the datasheet. You see here the number, theta junction ambient, 60 degrees per watt. That's valid if the IC is mounted on the GESD 517 PCB. That's a standard PCB with a defined size. If the IC is mounted on our evaluation board, the theta is lower to 45. What you can see here, the theta in the data sheet is only valid for the PCB where it has been measured. So these numbers here, they have nothing to do with your custom PCB, nothing. They are wrong. They can be higher or lower depending on your PCB size. Here we see a typical application of the MPQ 4572 DC-DC converter with a 5-volt, 2-ampere output. We take this IC as example in the webinar. What is the junction to ambient thermal resistance, theta junction ambient? Theta junction ambient is defined as the thermal resistance from the junction to ambient temperature. It is a measure of the device's ability to dissipate heat from the junction to ambient temperature via all heat transfer paths, the sum of kappa drags, vias, and air convention conditions. Theta junction ambient is only valid for its defined PCB. It is a common mistake to believe that theta is a constant that can be used on all PCB. That sentence you have to keep very good in mind. Theta is only valid on the PCB where it has been measured. Theta junction ambient allows for a comparison of different packages on a common PCB mostly measured on the GSD 5171. You can find this PCB as an image on the JEDEC.org website. So the theta value is only for compare package A with package B in case if they are mounted on exactly the same PCB. For example, if you have a package with 3 × 3 millimeters, package A and B, if one package has a lower number, then you know this package is a little bit better than the other package of the same size. That's the message of theta, nothing more. What is the junction to ambient thermal resistance theta junction ambient? On the right, we see an evaluation board for the MPQ 4572. It is a 4-layer board with a size of 9 × 9 centimeter. Theta junction ambient can be calculated with equation 2. With the example of 1.1 baud at an ambient temperature of 25 degrees, we get a junction temperature of 91 degrees. But this equation is only valid exactly on this evaluation board. Theta junction case is defined as the thermal resistance from the junction to case temperature on the bottom of the package. This temperature is measured close to the pins. Calculate the junction with theta junction in equation 4. Heat flow is the heat flowing from the junction to case and can be estimated with equation 5. The figure here shows why theta junction case cannot be used on a custom PCB. In the example, heat flow is separated in 2 paths. One is going via the package to the top, and most of the heat flowing from the junction into the PCB. The heat flow is just like a current source in this electrical circuitry. The theta junction case is unknown for the custom PCB. Heat flow that radiates via convection from the surface of the package to the environment. Every custom PCB is always different from the GSD PCB. The dimension is different, the cover is different, the number of layers often different. The purpose of theta junction case is to compare the heat flow of different packages in case if they are measured on the GSD PCB. The actual heat flowing from a custom PCB is always unknown. Only a standard PCB like the GSD has already had this parameter measured. What are the thermal characterization parameters for Psi junction to case top and Psi junction to board? Psi is described in GSD 51.2a. Psi can be used when the designer knows the total electrical device power. With Psi, the user can directly calculate the board's temperature the junction temperature. Psi is a characterized parameter and allows the calculation of the junction temperature using a thermal image camera. Measure the package top surface temperature with the camera and calculate the junction temperature using equation 6. The advantage of the Psi parameter is the power in the device you can measure with the oscilloscope, current probe. You multiply it, current and voltage on the scope, then you have the power. You add the surface temperature, the ambient temperature, and you multiply the Psi parameter, and this will lead exactly to the T junction, very close. And this equation is almost valid for all custom PCBs. The Psi depends on the air convention. So it is measured on a free PCB where the air can rise up free. A typical value for Psi junction top is between 0.8 degrees per watt for a thinner package and 2 degrees per watt for a thicker package. See equation 8. The T position 1 minus T position 2 is the temperature difference between top package and junction. P device can be easily measured with test equipment. With the thermal camera or a sensor, for example, a PT1000 on top package, the junction temperature can be measured. Compare with equation 7 for theta. This method is not possible because for a custom PCB, theta is in most cases unknown, and also the power in a specific path, impossible to use it in a practical manner to calculate your junction temperature on your custom PCB. With 7, it's almost impossible. You don't know the parameters. For 8, it's possible. Calculation with thermal networks. A thermal network can be converted into an equivalent linear electrical network. Theta junction ambient is the name for the equivalent thermal resistance between the junction and ambient air. What you see here is approximately a circuit, a thermal circuit for an IC mounted on a PCB. You have in the middle the silicon die where the heat is generated, one path to the ambient, the Psi here, and the nice thing here, this Psi here can be specified, and this allows you to measure the junction temperature in case you know this top temperature here, measured with the thermal camera or with the PT1000 or any other method. And then you just multiply it with the Psi. It's around 2 or 3 degrees hotter, the silicon compared to the top of the surface. It's depending on the thickness of the package. The other way, if you want to use theta, it's very difficult because you have to know all these parameters and calculate it. The calculation, it would be easy. The circuit is not difficult, but you don't know the resistors. So you don't know what to enter in the equations. So this picture here is only for demonstration. Where are the thermal resistors and how it works? Here inside the copper, the thermal resistors are very low. In the VR, it's low. That one here is high. That one here is also high, but it's the only one to remove the heat to the ambient. The ambient is the ground here. You can use the theta only if it has been measured exactly for your custom PCB. And in most cases, you don't have this number. Calculation with thermal networks. Thermal resistance, heat flow, and temperature difference described the thermal steady state. This is the point of interest. If you heat a PCB for 5 minutes, for example, you are interested in the final temperature. If you are adding the heat capacities, you can calculate the transient response. It is often done for a large heatsink to see how large the heatsink have to be. For example, for 10 minutes power time. Level of decrease, level of detail increases network. You get a complex calculation. Remember the circuit, it's very hard. You don't know the variables exactly. Hardware developer lacks precise information about dimensions, material constants, and heat flow. Difficult to calculate. The best way, layout and thermal programs can graphically represent the heat distribution via finite element calculation, a good choice to avoid larger mathematical calculations. Here we see a layout of a DC-DC converter. Make the metallic heat transfer path between the IC and copper plane as short as possible. This means you see here the heat, the die. The white area has 77.4 degrees. That's the area of the high side and the low side MOSFET. They are the most hot part of the silicon. On the left, you see an area which is a few degrees colder. Here is the control unit of the silicon. And then you see the best heat path are the ground pins, the V-in pin, and the switching node pin. All the pins which are connected directly internally to the power MOSFETs, they are the most important ones for the heat flow. You see here the switching, the inductance. It is very close on the switching node. It's that small yellow one here. Because this area have to be very small, this polygon, because of EMC. It's a fast changing voltage. And the inductance acts as heat sink for the silicon. Heat will flow on this short way to the inductance, will heat up additional the inductor, and this cools down the IC. The next heat path is here from, I don't know if it's a ground pin or a V-in pin, to this vias here, to the via1. The via1 sees a large temperature difference from yellow to blue. And this via is bridging a lot of heat into the bottom layer. So the via1 transfer more heat into the bottom layer than, for example, here, the via2. via1 has a higher copper temperature difference between the top and bottom layers compared to the colder via2. via1 can transport a greater heat flow between both layers. So therefore, place the vias close as possible to the pins, but not too many of them, because when you have here only vias, then you have a lot of holes. And if you have here many holes, the very worthful top layer is reduced in kappa. So you have to find a good balance between the number of holes of the vias and the top layer. The top layer is the most important one to dissipate heat. Another good method is here, you see here this green here, it's a polygon, it's the V-in. The V-in is the stable input voltage. And this stable input voltage polygon can also be used as heatsink. So in this circuit here, we have now 3 dominant heatsinks. That's the V-in polygon, the thermal vias, here and here, the top plane for the ground around, and the inductance. That's the only chance how to cool down the IC. For example, also here, these control pins, they are not to the MOSFET here connected. Make it also a little bit big when it's possible. It will help additional to cool down the IC. Layout recommendations: large copper heat path near the IC. Avoid cutting planes with unnecessary conductor tracks. That means don't route any other wires directly to the IC. You will cut the very good heatsink of the top layer. Top and bottom layers are best to radiate heat. Avoid thermal reliefs on SMT pads, especially for the ceramic capacitors. They are large, and most pick and place machines and soldering machines nowadays, they don't need the thermal reliefs anymore. GND unstable potentials are best places for thermal vias. Filled capped vias directly under SMT pads improve the thermal conductivity. Of course, if the via is directly under the pad, it's perfect to transfer the heat directly from the pin into the PCB, to the inner layers and to the bottom layer. But of course, that technology costs more money if the via have to be filled and capped with copper. It's depending on the project if you have this margin for the bill for the price. Avoid vias for fast signals, the switching node. This worsens EMC performance. A PCB from FR4, the epoxy resin and glass fiber, has a low thermal conductivity. So the PCB, it has only a big surface, but it's conducting very bad. This means bring the copper close as possible to the IC, and don't think the PCB will help you much. If there is not much copper on the PCB on the top layer, if you don't have thermal vias, the big PCB helps you not much because the thermal conductivity is bad of epoxy. Okay, some certain PCB materials are available. They have a better glass fiber and epoxy resin. Factor 4 to 8 times is possible. A question of the PCB manufacturer, what he can offer. As conclusion, the MPQ4572 from MPS was used to show how thermal parameters are analogous to electrical quantities and networks, and that both can be converted into one another. The electrical quantities often used by engineers enable a quick understanding of the thermal parameters in the interactions between a PCB. Thermal resistance parameters, which are commonly listed in a device's data sheet, allow designers to compare between the thermal characteristics of different packages. characterized thermal resistance, Psi, allow designers to calculate the junction temperature for custom applications. A thermal measurement on top of the IC surface makes it simple to obtain an accurate junction temperature measurement. So please let us know your questions. Visit our website. There are many more articles and videos. Questions are welcome now.
Thank you very much, Ralf, for the great presentation. I would like to remind every one of you that you can mouse over the bottom of your Zoom webinar interface and you will see the Q&A button. Please type in any questions that you might have. As we are waiting for questions to come in, I want to remind you that we are recording this session and we will send you a link early next week. With this link, you can watch today's webinar on demand, and we will also send you a link to the presentation itself. So let's get started with the first question.
Okay. So do you have, yes, I can read. Do you have a recommendation for thermal simulation software? No. It's depending on your layout software. In case, if you use Altium, they have included a thermal simulation as a module which you can buy. And for the other programs, it's the best ask the manufacturer of the layout software, because the layout software and the thermal finite element simulation, it must be in the same system. Otherwise, it's becoming difficult. Julian, you can continue with the questions.
Yeah, I will continue now. So, Ralf, how much improvement is there when filling vias with solder paste? When vias are used to connect top and bottom layer copper compared to vias that are unfilled? Vias not under components, but free vias.
In my experience, when I did layouts in the past, it's much. If you have, I don't have the numbers in my mind, but if the via is under the pad, you save some half a millimeter distance, and the via is directly under the pin. Is the big advantage. And the next big advantage is the layout is much more easy to done. The vias, often they are disturbing the layout. You have no space. When they are under the pads, it's perfect. And you can also place the components closer to each other, which is good for the thermal. And it's also very good for the EMC. But the only problem is the price. In my experience, the price of the PCB, it rises up around 30%, something like this, 30 or 40%. Of course, it depends on the volume. It's a matter of the product. Some products, some engineers, they would be very happy if they could reduce the junction temperature, but for example, by 10 degrees or 5 degrees. And they have the margin in their project, but for many projects, it's not possible.
Thank you very much, Ralf. So the next question came in via the chat. Hello, what is the preferred via layout? Few big thermal vias or more smaller? What is the preferred size of the holes?
One moment, please. I'm just opening the chat. I really don't know, because I would say you have to calculate the diameter and you have to ask for the thickness of the copper cylinder. And then you have to calculate the volume of this via cylinder of the copper and compare. Then compare a big via with, for example, with 3 small vias. You have the cylinder copper of the big via compared to the 3 small ones, and the bigger one with the more with more copper, I think it should be better.
Thanks a lot, Ralf. So the next question is it possible for a component to know its psi values?
Moment. For a component, I think you're talking about the IC. We specify it, but not for all parts. But you can ask us for almost all ICs. We have the psi parameter. We have a thermal simulation team, a package team, and they can give you the numbers, and they can also answer your questions for details about the specific IC.
Thank you very much, Ralf. So the next question, where to find thermal parameter psi?
We have them in the newer data sheets. For the older parts, ask your FIE. You can get in contact with the thermal simulation team and they give you the numbers.
Thanks a lot, Ralf. So I want to remind every one of you that you can type in questions in the Q&A button at the bottom of your Zoom webinar interface. So if any one of you has a further question, please type in the question now. So one more question came in. Why psi is the better parameter compared to theta?
Because psi is valid for almost all custom PCBs, because it's characterized on a PCB with a free airflow, and the theta is measured only exactly on the PCB where it has been measured. And in the most cases, that's the GSD standard PCB with a defined size extra for this measurement. And your custom PCB has never that dimension, never that copper, never that routing. The theta, the purpose of the theta is to compare package A with package B. And the one with the lower number with the same package size is a little bit better in thermal items, can have a better heat flow. That's the only purpose of theta. Of course, as explained, you can use the theta for the calculations, but it's becoming very difficult. You don't have the parameters. That's the problem, and the psi is much more easy. In the practical, the best is you use a thermal camera. The emissivity of the black plastic of the IC is around 0.995, and most thermal cameras can be adjusted to that value. Normally, they are pre-adjusted to 0.95, and this means the camera measures really exactly the temperature of the black plastic of the IC. If you want to have it very accurate, spray the PCB with a special thermal paint. The manufacturer of the paint has specified the reflection factor, and then you can adjust it in the camera software exactly to the parameter in the data sheet of the paint. And then you know exactly the top temperature. The power inside of the IC, you can measure it easy at the electrical power and then just multiply it with psi value. But as a rule of thumb, most people, they know it, the junction temperature is almost the same what you measure on top of the IC with the thermal camera. With a very thin and small package, it's becoming even much more closer compared to a thick package.
Thank you very much, Ralf. So one more question came in. How to convert tether of standard PCB to tether of custom PCB?
You have to do a measurement, and this measurement is described in the GDEC.org organization website, how to do it. I've never done it by myself. We, in our company, also the package team and the thermal simulation team, the people do it there.
Thank you very much, Ralf. So another question came in. Do you have an example of a calculation with thermal capacities, EC, in order to calculate the temperature rise during a short pulse?
For myself, I only made it for a large heatsink, for a big aluminum copper heatsink. But I think the question here, it goes for the small mass of the silicon. I never made it. I know only the silicon has a time constant in the range of a few milliseconds only. This means a pulse of a few milliseconds is almost like a DC pulse. It's depending on the die size. A good idea for that could be, if you want to know it on the DC-DC converter, you can use the body diode of the MOSFET, of the high side or of the low side switch, and calibrate the diode voltage with a current, also the reverse, the body diode, and then switch off fast the current and measure the voltage drop across the body diode. Then you see on the oscilloscope the exponential function. And from that function, you can recalculate the time constant. It's only some milliseconds. It's short.
Do we have any other questions?
Yes.
We will pause here.
Mostly passive coolers are placed on top of the IC package. Wouldn't it be better to place the cooler on the bottom side of the PCB? Just try it. Yes, I would say yes. If you because most of the heat will go via the pins into the PCB, and when you can cool down the PCB, I think it's the better way. But it's much more difficult to mount. It depends if you have the parts or not. On top, you can just glue it. It's a matter of trying it, of experiments at the end.
Thank you very much, Ralf. Any further questions? So if not, I want to remind you that we will send out a link to the recorded session early next week. Please make also sure to check our webpage for webinars, which will come in the future. And I want to thank every one of you who joined this webinar today. And as I said, check our webpage for more information.
Thank you for joining the webinar. Welcome at MPS.